Yeah, so in this video I'll show you how to back calculate C7 plus molecular weight and C7 plus specific gravities from measured stock tank molecular weights and stock tank APIs. It's a very important plot to create for a field, essentially because it exhibits the trend of relative periphenicity and aromaticity of a fluid system, which is important for C7 plus characterization, which is an advanced topic discussed in the advanced equation of state fluid or PVT and equation of state fluid characterization course. I guess what's important to emphasize here is that there are typically a lot of C7 plus molecular weights and specific gravity numbers that are reported in different PVT studies, but most of the times they're actually calculated based on the specific gravities and molecular weights from cat spheres of the body. And we'll look at the differences that sometimes can be small and many times can also be very, very large. So it's very important that you actually do this back calculation yourself to convince yourself that for your particular case they're either small or large, and no matter what you do, there's always these molecular weights of C7 plus and specific gravity of C7 plus that you back calculate with this particular exercise and procedure that you are going to use for your particular field that you study. So just re-emphasizing that this guy right here is measured stock tank molecular weights, and we have measured stock tank APIs, not calculated values. And the other thing is that we're not working on the reservoir fluid, we're working with the stock tank oil molecular weight. And the stock tank oil molecular weight can either be obtained from a single stage flash of the reservoir fluid, or it can be from a multi-stage C7p test. And if you have both of them available in the same test, you can actually get 2 different points on this particular curve. The 2 cases that we are working with, we have a gas condensate PVT report and a black oil PVT report from the same basin, which will essentially give us two different points on this curve right here. So for instance, this could be the gas condensate PVT study, while this could be the black oil PVT study, for instance. So for a particular field, we expect these values, no matter what if the GORs and everything can be very, very different, or you have sampled in different points in time, that this trend is and remains consistent. Good. So going over to the Excel sheet where we'll essentially do the exercise. So I've helped you all a little bit and essentially digitized, or we've provided the digital version of the flashed oil liquid from the black oil study and the flashed oil from the so-called gas condensate study that we have. As I mentioned, we are going to use measured values. We're going to use measured molecular weights, measured stock tank APIs, but we are also going to use what's measured in terms of compositions, which we agreed is not mole fractions, but it's mass fractions. Great. So the first thing we'll do, just to have done that, and these are the values that are most times reported by the lab. That's the lab C7 plus molecular weight and specific gravity calculated with the cat spheres of body molecular weights and specific gravities for each component. Averaging of specific gravity and molecular weight, these formulas, the basic formulas are given to the right here. So if we would like to average from, for instance, C7, we need to do the averaging from C7 up here and also below. So I'll show you how that is done right here. So we use this, so first we're going to do this for the reservoir oil. We're going to use this formula to the right here, which is averaging of molecular weights. So we're going to sum that up all the components heavier and equal to C7. We're going to divide that by the sum product of the same compositions, but we also need to do the multiply with 1 over the molecular weights of each of those components. Perfect, and we get 263.6, and we're going to compare this number to when we actually use the measured values a little bit later. As we see here, which is lucky for us, the averaging of molecular weights and specific gravities, the equation is very, very similar in terms of call it mechanics, but the only difference is that we use for averaging of specific gravities, we use the specific gravities of each component instead of the molecular weights. So we can simply just copy paste this formula right here into the next cell. Again, still working on the flashed oil from the reservoir oil, and we just change to specific gravities and we get 0.854. We can continue doing the same exercise, but now we're going to change focus to the gas condensate just to make sure that we do both at the same time. Remember that we need to change the composition, the weight percentage, and use the relevant molecular weights here. The reason why it's important to use a different column of molecular weights is that what's reported in terms of the heaviest pseudocomponent from the laboratory is different in these cases. However, if we look at the other components, except from the C26 plus, they're the same. So that's just like an FYI. And again, when we've done this for molecular weight, we can do the same for specific gravities and just change the column to specific gravities. And now we have the C7 plus molecular weight and specific gravities calculated with these cat spheres of body molecular weight and specific gravities here and here, that's provided by the laboratory, which for C7 plus components are in general arbitrary values, or they're not necessarily representative for the reservoir or for the system that you work with. So now we're going to do essentially this back calculation exercise for both the reservoir oil so both the reservoir oil and the reservoir gas, or the flashed oil products from both of those cases. And again, that's to make sure that we get 2 points on this particular curve right here. So for instance, this point right here and this point right here. Good. So going back to this, to do this back calculation, we need to apply the formula to the right here. And for those of you who would like me to derive this equation, send me an email at carlson@whitson.com, and I'll make sure, if you would like to see it, I might add it to Whitson Academy, or I'll send you how it's done, or you can try yourself to derive that equation from just using the definition for averaging right here. But the trick is that we have essentially applied this formula at the top here, such that when we back calculate the molecular weight of C7 plus, all the input parameters here are measured. And we know that because the average molecular weight is measured, the component mass fraction of everything up until C6 is measured. The molecular weight of the non-hydrocarbons and the hydrocarbons up to C6, they're known, their molecular weight is known, it's given to us by Mother Earth, because there's, like, the isomers are given on a discrete basis here, while the molecular weight or the mass fraction of what's heavier than C7 plus is also provided to us right here. So in that sense, it's very, very nice. So what we'll do is to simply just apply that formula right there. We need to sum up everything that's heavier than C7. So that's either just to sum up that column right there to C33, or it's to do 100 minus everything that's lighter than C6 is the same thing. Then we do 100 divided by the average molecular weight minus the sum product. And now we need to remember that we're going to use the things that are lighter than C6 or lighter than C7. So we need to take the sum of everything that's lighter than C6, and then we need to do 1 divided by the molecular weight up to C6, like that. And again, we're lucky. We have a very, very similar equation for specific gravities, and we can simply just move this column over to the right, I thought. And we also need to change the average density. So now we're applying this formula to the right here. And we see we get a slightly higher number right here, which is I guess expected. We'll do the same exercise for the gas condensate, so we can simply just copy paste this formula, make sure that we move the relevant cells to the other side. It doesn't really matter if we change the molecular weights or not, because these are known components, so this column and this column is the same, but just for clarity I'll move the column over. We also need to change the average molecular weight here to 160, because that's the average molecular weight that's measured for this gas condensate. Well, excellent. So now we get 189, and again we can apply the same formula for specific gravity, but now we have to remember to use the specific gravities of all these components, and also change to the measured specific, or this is actually, that's a good point, that maybe some of you guys reacted on that this is not API and it's not specific gravities, but it's actually the densities in grams per cc, but it's very close to specific gravity. So if you want to be a little bit more accurate, you can convert this to specific gravities by which is almost a 1-to-1. And if the only thing you have available is an API, you need to apply the formula for API conversion. So what we have at this point is essentially this relationship right here, and this relationship, or this point right here. So that's the 2 points that I talked about on this particular curve right here, right? The other thing that's interesting to note is that we can compare these numbers to the ones that was calculated by Katzver-Zabadi. We see that they are similar, but they're not the same. And in some cases, they can be radically different. And in many cases, they actually are. And the same goes for the gas condensate case right here. We definitely see that they're not the same numbers, and which is expected. And the back calculated numbers are the ones we should use.